So yeah, just thank you everyone for joining. This is really a very interesting presentation. I have a big interest on air quality, as I'm sure all of you do. And Gabby and I are part of a science panel with the Department of Health and Environment. And through that panel, I got to learn about some of these really amazing research that is happening here in Colorado. That is really something that is really amazing for not only the country, but for science at large. You know, so I think it was something that I thought would be very beneficial for us to share in this Rocky Mountain State Section monthly meeting. So I'm very glad to have them both. So let me give an introduction. I mean, the name of the presentation is Air Quality, Bringing Research into Decision Making. And if you guys can help me, I know, Andy, if you're on the call, could you accept people as they come in? So anyway, so let's start with the introduction. So first we have Gabby Pfister, who received both her master's degree in geophysics and meteorology and her doctorate at the Karl Franzens University in Graz, Austria. Hopefully that was close.
Close enough.
Thank you. At the postdoc at the National Institute of Water and Atmospheric Research in New Zealand, she came to NCAR in 2002 under the Austrian Erwin Schrödinger Fellowship. And she remained at NCAR and is now a senior scientist and also serves as a deputy director for the NCAR Atmospheric Chemistry Observations and Modeling Laboratory. Gabby's research revolves around the field of atmospheric chemistry and air quality. She both develops and applies regional and global air quality models, and she also has used satellite retrievals of atmospheric composition and observations from field campaigns to successfully integrate modeling and measurements in her research. One of her most notable achievements has been the co-lead of the Front Range Photochemistry Experiment, FRAPPE, which I'm sure many of you may have heard of. A major and successful field campaign along the Colorado Front Range in July through August 2014, with a focus on studying summertime ozone pollution, which is one of the most important pollutants here in the Denver metro. Rajesh Kumar is our other presenter. He received his master's degree in physics from the Kurukshetra University in India and his doctorate degree in earth sciences from the University of Hamburg in Germany. He came to NCAR as a postdoctoral fellow in 2013 and stayed at NCAR after his postdoctoral fellowship. He's currently a project scientist 3 in the Research Applications Laboratory, and his research focuses on air quality. That is one of the most important socioeconomic and environmental concerns around the world. He synergistically integrates ground and satellite-based air quality monitoring with atmospheric composition and modeling capabilities to address a number of air quality issues, including transport and transformation of air pollution, the relative importance of local and foreign emissions, deterministic and probabilistic air quality predictions, aerosol-climate interactions, heterogeneous atmospheric chemistry, chemistry-climate interactions, projections of future air quality, and impacts of air quality for public health and food security. One of his most notable achievements has been the development of an operational air quality forecasting system for New Delhi that has been helping the decision makers cut peak pollution since 2018. So thank you both for being on our meeting, and I'll turn it over to you, Gabby. Thank you.
Well, thanks so much, Sergio, and everybody. Both of us are very pleased to be here. Thanks a lot for inviting us, and just give a little bit of a quick insight into some of the work that we are doing that specifically is focused on applying our research to decision making and policy making. Most of you. Let me just, no, it moves, sorry. Most of you are probably familiar with NCAR. I just wanted to bring up in 1 minute a slide on what NCAR is. NCAR is located in Boulder. It's the National Center for Atmospheric Research. We are a federally funded research organization, which means we are not a federal organization, but we do receive funding from the National Science Foundation in parts. A main mission for NCAR is to conduct science with and for society. And we have 7 different labs that range everything from instrumentation to I'm in the chemistry lab, to climate, to space weather, and computing, as well as Rajesh is in RAL, which is the Research Applications Lab, where you really are focused on bringing research products to applications. So that's NCAR. And now let's move on to our talk. What can you expect to hear in the next 45 minutes? We'll start just with some very, very basics on air pollution. Hopefully I don't bore too many of you, but we just want to make sure that some of the basic concepts are understood. And then we bring examples of field campaigns, and Sergio has mentioned already FRAPE. And they also want to just touch briefly on satellite data. And Rajesh will then focus mostly on modeling applications that ranges from forecasting to reanalysis to climate predictions, and also then end with a pretty exciting or very interesting study that evaluates the mobile flux plane method, and he will explain that later. So let's get started with some basics. Air pollution is not just one compound that's out there. It has several components, actually a lot. First of all, and most of us are probably familiar with the 6 criteria pollutants. And in addition to that, we have to deal with air toxics, volatile organic compounds. And there is a lot more besides that, but these are the major ones. And they come from all different types of sources, and frequently one or more of these pollutants occur together, and some of them share the same sources and some just don't. So it's just a pretty complex picture. So the 6 criteria pollutants, these are carbon monoxide, sulfur dioxide, nitrogen dioxide, lead, ozone, and particulate matter. And all of these criteria pollutants have negative health effects, and they are regulated in the US by the Clean Air Act. The other distinction when we look at pollution is that we have to look at primary and secondary pollutants. A primary pollutant is directly released from a source into the air. So you can expect that the largest impact will be seen near the source, and then it will start getting transported away, being diluted, mixing, and the concentrations will get less. Secondary pollutants, such as ozone, which is the biggest culprit in the Colorado Front Range, they are formed chemically in the atmosphere from what we call precursor emissions. So something goes in the atmosphere, and then in the atmosphere you create this pollutant. And that already tells you now that the impact of the secondary pollutants will be larger away from the source and not the highest right next to the source. And so that makes it really complex to make this connection between where does the pollutant come from. I probably don't have to tell you why we are concerned about air quality and pollution, because of the large health and environmental impacts. There is just, I'm not sure if you can see my mouse, but definitely a big impact is on human health. There is a lot of additional impacts also on land, water, and the entire ecosystem that's of big concern and makes really air pollution one of the biggest hazards globally. There is actually an interesting, and I put the link to the internet here, is in 2011, EPA looked at the results of the Clean Air Act and looked at that over 20 years and wanted to see what's the benefit of that in regard to human health. And according to this study, the central benefits of the reductions in pollution because of the Clean Air Act, they estimate that the benefits exceeded costs by a factor of more than 30 to 1, something in the order of 2 trillion compared to 65. So because you improved people's health, you reduced premature mortality, you had significant health savings. And this Clear Air Act has really helped us to clean up our act. And we can see that also from space. And here what I'm showing you is an image of the AWMA satellite instrument that measures NO2, nitrogen dioxide. And this image shows you an annual average for 2005. And now we can move on to 2019. And you can see there is significant reduction. There is a lot less NO2, which comes out a lot from cars and also power plants. So again, here, 2005, moving on to 2019. And we can also see that in the Denver area, when we look at the time series going for the same time period from 2005 to 2019, and you can see how the NO2 levels also in Denver have gone down. But if you look at the recent years, it also starts to level off a little bit. So we are not continuing in this significant downward trend. But because of the reduction in the pollutants that we have seen, we have also a significant reduction in the number of days that reach unhealthy levels and that are above the air quality index. So, and this is here just again from the US EPA website, a diagram that shows for 2000 to 2020 for all the 35 major US cities, the air quality days with bad air quality. And you see again here that they have been going down, but again, over the last years, it's kind of just going up and down and rather stayed stagnant. And so does it mean that, you know, our pollution has improved, so we are fine and we are going home and we all have lunch? That's not going to happen, because if we look at the number of people that live in counties in the US where the air quality levels are above the national health standards, which we call the NACs, then you can see that there is still nearly 100 million people are still living in areas where they are breathing unhealthy air. And the biggest issue in the US is because of ozone. So yes, we have had a success story. We just have not made total success yet. We still have some ways to go. In Colorado, Sergio also has mentioned it, and ozone is our biggest issue. And Colorado, specifically the Northern Front Range, is actually a serious non-attainment zone, which means, and so you can see that here all across the US, there is a lot of non-attainment areas in California, some in Texas, some on the East Coast, and here is the Colorado Front Range. So we really need to get our act together and clean up our air for ourselves, and also because the law requires that. So what is ozone and how is it created? Well, in a very, very simplified way, what you have is you emit from a lot of different sources. These are cars, industry, even vegetation, a lot of household activities release volatile organic compounds, and we call them WOX, or nitrogen oxides, NOx. You put them out into the atmosphere, you have a sunny day, you have sunshine, and you create ozone. And so it wouldn't take much research if it would be really that easy. It's actually quite complicated, because at the same time, you have interactions with a lot of other chemicals, you have interactions with clouds, you have production, you have loss, it gets moved around in the entire atmosphere, it gets deposited on the ground. And even what's shown here as very simplified chemical production is actually a pretty complex chemical reaction scheme, which even these diagrams show it only in a very simplified way. So there is a lot of research that needs to be done to really understand and characterize all the different processes that ultimately lead to how much ozone we find and breathe in. Now, air quality management has actually a problem in that regard, because what operationally is being measured is at a number of surface sites. And here I show you a map of ozone monitors across the US. You measure ozone and PM 2.5. And then you measure also somewhat NOx. The measurements are not always perfect. And maybe also carbon monoxide. And you have a few measurements of volatile organic compounds at some locations. But you really don't have a whole lot that you can work with to understand what's really causing the pollution that you find in the air. So, and all these measurements are done at the surface, but the atmosphere doesn't care. I mean, your pollution doesn't stay at the surface. It all mixes around. It all gets transported around. And all the processes are time dependent and many are nonlinear. Plus, we are not just having a VOC and PM 2.5. VOCs are actually comprised of hundreds of different species, and they all have a different role in ozone chemistry, and they all are emitted from different sources. And the same issue or the same challenge you have with PM 2.5. And because the chemistry is nonlinear, but it also means when you reduce precursor emissions, you are not necessarily decrease your secondary pollutant. And so sometimes you decrease a precursor emission and your secondary pollutant actually goes up. And that's also not what you want. So you need to be really smart when you want to come up with policies to reduce pollution. So it requires scientific knowledge to know where and how to reduce emissions. You don't want to just take a blind shot and hope that it goes well. And this is where I bring frappe in now. And I apologize, some of you might have heard talks about it before. So I just want to bring a quick overview of some of the results that we had from these really major field campaigns between the state, EPA, NCAR, NASA, NOAA, the National Park Service, universities. A lot of players came together in 2014 in the Colorado Front Range to look really into the question, what are the drivers behind high summertime ozone in the Front Range? And that was the major question that we addressed, but there were also other questions that frappe looked into, such as into air toxics. There was work being done on methane and also on nitrogen emissions and impacts on Rocky Mountain National Park's ecosystem. But in here, I'm just focusing on some of the work that was done in regard to ozone. Field campaigns are a significant benefit in addition to surface measurements, because specifically when you have a number of aircraft like we had, towers, balloons, mobile vans involved, you can really gain a 4D picture of the atmosphere. And all of these platforms that we deployed had a huge set of instrumentation on board. So you really got measurements of primary, secondary pollutants, intermediates, the products, and also a very well characterized meteorology. Just a little bit of snapshot of what can you see from an aircraft, for example. So here is a map of the Front Range. And you can see, I hope you can see the Denver metro area. Then you see all these pink dots. This is Weld County, where we have a lot of oil and gas and also agriculture going on. And the colored points, this is the aircraft measurements of ethane. Ethane is a compound that's mostly released from oil and gas activities. And you can see that you really have the highest concentrations in the area of Weld County. And this was a day when also during the day we had, as frequently happens in summertime, we had upslope flows. And you can see that that high ethane that's released in the oil and gas area is being transported up into the mountains with these upslope flows. Nitrogen oxides are mostly released from traffic and also from industry. And there is some high concentrations in Weld County, but the highest concentrations for nitrogen oxides we really find in the Denver metropolitan area, where we just simply have the largest concentration of traffic. And again, here you also see that with the upslope winds, how this high nitrogen dioxide that's released in the Front Range is being transported up into the mountains. Now, for ozone, since that is produced by nitrogen oxides and volatile organic compounds, we get a much more complex picture where we see high concentrations around the Denver area as well as around Weld County. But you also can see that during the transport into the mountains, there is obviously a significant amount of ozone being produced. So we use data like that, not only from the aircraft, but also from the ground and a lot of other platforms to use these to improve, first of all, the emissions. That's a significant input that we need. We need to know really what's coming out before we can go any further. And so what we do is we take activity data that are available from EPA and CDPHE, develop the best estimate emission inventory based on these activity data and other assumptions that typically agencies have, and put that into an air quality model. And in this air quality model, you put the emissions in, then you have basically the weather is simulated, the transport is simulated, everything is simulated. And you have a 4D field of concentrations. And then you compare that with the observations that you have from the field campaign. And you will be off. You will not look right. So then you start an iterative process. You modify the emissions, see if you run the model again, do you get a better agreement with the observations? And you do that in a pretty smart way until you get the optimal agreement of the model and the observations. And when we did that in our work, what we found was that, first of all, the traffic actually outside of the traffic in the Denver area seemed to be pretty well represented. The Denver outside of the traffic area, we had to at least double to make things match with the observations. The other one was also that oil and gas was, specifically volatile organic compounds from oil and gas, were significantly underestimated, and other studies found some similar results. And we had to at least double the emissions from oil and gas. And even that was kind of on the lower conservative side. And there was a number of adjustments that needed to be made to other species. So now, and there's a lot, this chart looks simple here. There was a lot more work to be done. But basically what we ended up with, we had the best possible emissions. We had a really good representation of the metrology. There was also work going into. We also did a lot of very detailed work to really understand the chemical processes and make sure they are well reflected in our model. And then we can take, actually, once we have a really robust model that we have confidence in, then we can use the model to play games. And in that way, what we did was we take the model, we run the model with all the emissions in the front range, and then we say, stop, nobody is emitting anything anymore. We have no more human caused emissions in the front range. What's the difference? By how much would our ozone go down? And that you can see as the contribution. And when you do that, you find that on high ozone days, the locally produced excess ozone can reach up to 40 ppb and more, easily exceeding the NEX. So it was really clear from this exercise that it's really the emissions in the front range that are our biggest issue in regard to high ozone pollution. And it's not coming from somewhere else or something. The biggest issue is really our own activities in the front range. And we also did the same experiment and looked at various emission sources, different sectors, and specifically on oil and gas, mobile, industrial, and power plants. And what you can see is really overall, the two biggest major factors are oil and gas activities and traffic. And this is really something that we need to address and reduce in order to deal with the ozone problem that we have in the front range. Now, models have uncertainties, and we are researchers. Everything has uncertainties. Nothing is certain. There is never 100% uncertainty with anything. So we wanted to make sure to test really how good our conclusions are in using this air quality model. And for this, we used a chemical box model. A chemical box model is basically just one box, and you put emissions into the box. You have a very, very complex chemistry in there, much more complex than you can have in any 3D model, in any air quality model. You exposed it to sunshine and you let it cook. And what we did is we constrained the box model by the measurements and not by any other emissions or whatever. So it was really constrained by measurements itself. And we get actually very, very similar conclusions. And here is just an example from how much ozone you produce is a solid line when you consider oil and gas, and then we adjust it for the concentrations that would come just from oil and gas, and then you see you get a significant reduction in ozone. So I don't have really time in this talk to go more into details, but if you're interested how we did that, please ping me offline and I'd be happy to chat about that more. But the important part was that we used two very different independent techniques to evaluate our conclusions, so that when you go to stakeholders, that you can increase the confidence in the results. So now I mentioned that really surface measurements are important because they give you the longevity, but they are limited in space and complexity. Field campaigns are giving you extremely rich 4D picture, but they are a snapshot in time. I mean, I would love to be able to have frappe nonstop. Let's have, take all these measurements all the time, or at least once a year. It's probably not feasible. So what can we do to fill the gap in between and complement the picture? And this is satellite data. And satellite data, specifically for air quality, have really over the last 20 plus years, they have really become essential in any air quality management research and in many, many other areas. In the weather research, they've been already longer around. Air quality, dedicated satellite measurements, it's probably about 20 plus years. The data have really been used to characterize pollution sources, transport, and variability on weekly to monthly and regional to global scales. And instruments that have lasted way past their design lifetimes, they can give us now insight into air quality trends. Just an example, here at NCAR, we are leading the MOPIT instrument, which measures carbon monoxide. The first measurements that instrument took was in 2000. It was estimated it will have a 5-year lifetime. We have now 22. The instrument is still measuring. I always like to knock wood because let's hope it continues measuring. But that's really an amazing success story. And we have really a lot of information that we gain from these trends. Just one example for a more recent work where we can use satellite data for policymaking. And this is a paper that just came out in Science, and where they used AWMA, which is a European satellite instrument that measures methane and also NO2 and other species. And using those data, they were able to quantify very large releases of atmospheric methane by oil and gas ultra emitters. And when they did their analyses, they found that these ultra emitters represent as much as 12% of global methane emissions from global oil and gas production. And this is really something when you have results like that and you see the magnitude of these leaks and these ultra emitters, you can really think about how can you address that. And they show also that it could be actually mitigated at very low cost. So currently what we have is what we call the polar orbiting satellites. So they are going around the globe, and over one location at a place, they take one measurement. So for example, most of the measurements are done either early mid-morning or early afternoon, but only once a day. But that's why you have a global picture. Now, what's really exciting is the new type of satellite data that we will get is geostationary, which means they are over one place, stare down at one continent 24/7. And for the US, this is going to be TEMPO, the TEMPO instrument. And here you just see a snapshot of synthetic data. So that instrument is not yet launched. The instrument will be launched in a year, hopefully not much later. And that will give us over the US continuous data of ozone, of NO2. But of course, this satellite data will not give you necessarily the surface information, but you can deduce a lot of information about surface concentration from it. But again, it will give us continuous view of one place, for us, the US, which means in the future, we will be able to cover all scales. In the future means in a year or two. And this movie here gives you a feeling for how that is. So you will have a geostationary instrument, such as TEMPO, that looks over the US. At the same time, you have a polar orbiting that will give you the global view. And TEMPO over the US is not the only geostationary satellite. The Europeans are launching Sentinel-4, which is a geostationary satellite that will look just over Europe. And what has been launched actually already about a year ago is the JAMP satellite that will look at Asia. So now we have all these different satellites that will complement each other and give us really an amazing view of the atmosphere. So it's exciting times to be a researcher, and I think it's exciting times to be also a policymaker, because these data will be of extreme value for policymaking. So the pieces in the puzzle for air quality research and to really support informed decision making. We really need observations, and we also need field, and I haven't talked about them, but also laboratory experiments, so that we characterize conditions and understand the processes. And we also have seen already with FRP that models are really essential in the analyses and to interpret observations and to draw conclusions. But models are really also essential to predict past and future air quality conditions. I mean, we need to all know what to expect in order to be prepared. And we need to know how have things happened in the past and worked in the past in order to understand how to move forward. And this is something where we are changing a little bit topic now and go a little bit more deeper into models. And with this, I also hand over to Rajesh to take over and start talking about air quality forecasting as well as other topics.
Yeah, thanks, Gabby. Can you hear me clearly?
I can hear you well.
Okay.
Yes.
Yeah. So as Gabby said, means we use models for a lot of different purposes. And among those, forecasting next day's air quality is a very important one, because decision makers need air quality forecast for tomorrow and maybe 2 days in advance, 3 days in advance, to understand how the air quality is going to be in near future. And if there is a need to put some temporary emission controls to improve the air quality in the coming days. So this is a very busy figure that you see here, but basically you can break this down into 4 pieces of information. The first piece of information, which is mostly the boxes on the very left of this figure, is the observation information that is coming from surface-based stations, space-based instruments, as well as the emissions from natural and anthropogenic sources. We put this information into the second component, which is a wide range of models that we have to make predictions for the next few days. So once we put this information into these models, they give us air quality forecast for 2 to 3 days in advance. In fact, in some of the developing countries, decision makers are now requesting to get a forecast 10 days in advance, because they need to implement temporary emission control measures more frequently, and they need a lot of lead time for making those decisions. Once the models provide you the information about the air quality in the coming days, then these needs to be converted into something that is easily understood by the public as well as the decision makers. So we build a lot of products like concentrations, air quality indices, health impacts, and those type of things based on the information coming out of the models. And once those products are ready, then we go into the last step where we display them on a website or identify a different dissemination mechanism that is easy for both the public and policymakers. And then they use it to make decisions and protect public health from poor air quality. So next slide, please, Gabby. There is another aspect to it. The air quality science, it actually emerged out of societal needs in North America and Europe. And so it is natural that there is a lot of capacity to do air quality science in the rich countries or the developed world. But the developing countries are the ones that are facing the most acute air pollution issues right now. And therefore, to develop solutions in the developing countries, it is essential to have international partnerships between the developed countries and developing countries. And an example of one such partnership is the Delhi Air Quality Early Warning System that we developed together with the Indian Institute of Tropical Meteorology. And it has been providing air quality forecasts since 2018. And the top panel here, you see this partnership between NCAR and IITM. And on the bottom, you see a snapshot of the information dissemination system that we have put together. We predict air quality down to 400-meter resolution in Delhi, which provides us information about the air quality at neighborhood scales. Next slide, please. So in the Delhi Air Quality Early Warning System, we provide 72-hour air quality forecast. And in this system, we actually assimilate satellite-derived aerosol data of optical depth to improve the initial conditions for aerosol parameters. The figure on the top right here, we show how the assimilation of satellite data improves the air quality forecast. So these are PM2.5 mass concentration daily average from 10 October to 20 November 2017. And in this figure, the black line shows the observed daily average PM2.5 concentration. The red line is the model prediction without the assimilation of data. And you can see that the red line is always significantly lower compared to the black line, which means that if we do not provide any observed information to the model, it makes a large errors, and it is difficult for the decision makers to trust this model. So we assimilate the satellite data for aerosols, and we also allow the aerosols to interact with the weather parameters. And then we get the forecast in blue. So you can see for most of the days, the blue line is very close to the black line, which means that decision makers can put a lot of confidence into these forecasts. Now, there are some outliers too. So you can see that there is a peak on 19 October, which we were not able to capture. And this is because 19 October was the Diwali festival night. So people burn a lot of firecrackers. And these dynamic changes in emissions, we have not been able to represent those into the models. This was the first year, so we couldn't do it. But in the later years, we were able to implement an emission scenario for firecracker emissions and also capture these peaks. Another event occurred in the first week of November, where you can see that the PM2.5 concentrations daily average reached 500 micrograms per meter cube. And just for your information, the latest WHO guideline for 24-hour average PM2.5 is 15 micrograms per meter cube and 5 micrograms per meter cube for annual average. So you can see that the situation is really severe in Delhi. So on that day also, like although we were able to reduce the bias in PM2.5 by about 200 micrograms per meter cube, we were still not able to reach the peak. And since then, we have made several changes in the system, including going down to 400-meter resolution to improve the accuracy of air quality forecast. So on average, during this period, we were able to reduce the mean bias by 86%. And we were able to maintain this improvement over the 3 days. So even on the third day of forecast, we had an improvement of about 70%. Now, this was just a test period. And as we know that the air quality forecast, the day-to-day verification is very important. So we also look at a lot of measures on how good is our air quality forecast at the end of each season. So here on the bottom left, you see a table which tells us, depending on fractional bias and fractional error, how good the model predictions are. So if you see a green color, it means it's an excellent performance. If it is a blue color, it is good. And then yellow is for average and poor modeling performance. On the bottom right, you see the performance evaluation for hourly and daily PM2.5, as well as the air quality index. And you see mostly green to green and blue colors, which means that the performance was in the excellent to good range. Next slide. So we are making this forecast, and then it goes into the information dissemination system. But it is very important to understand how this is used by the air quality managers in Delhi. And this is one example. So air quality forecast, they go to Commission for Air Quality Management, which is appointed by the Supreme Court of India. And if there is a poor air quality predicted, as is the case for red arrow, then they put restrictions in place. And one example of this red arrow is this news article that is in the middle left in the Indian Express. So when the Commission for Air Quality Management shut down schools and colleges and put a ban on constructions. Depending on the air quality category, the table that you see in the bottom right, there are a variety of actions already defined. If air quality is predicted to be in severe plus categories, then they stop truck traffic entry in Delhi, stop construction activities, introduce odd even scheme, and potential school closure. So the example that you see in the newspaper was for an event where air pollution was predicted in severe plus categories. And through these restrictions, we were able to improve air quality by up to 20% during this event. Next slide. The decision makers, they not only need information about the air quality, but they also need where the pollution in a particular place is coming from. So to help that and implementation of the graded response action plan that I showed in the last slide, we have also developed a decision support system. And here is a snapshot of that system, which tells us the percentage contribution of emissions from Delhi, as well as all the districts around Delhi to air pollution in Delhi at a given time. So for this particular time, we see that only about 25 to 30% pollution in Delhi was coming from the emissions within Delhi. And more than 30% of the pollution was coming from the 3 districts that are located south and southwest of Delhi. So it gives important information to the policymakers on coordination with authorities from the nearby districts to implement the most effective emission control measures. Next slide. We also provide scenarios to the decision makers. So you see on the right of this plot the name of all the districts and all the sectors that we track into our modeling system. And decision makers can go and see, okay, if they want to reduce 20% emissions in a particular district or from a particular sector, they just have to make a click, and then they will get information about how much air quality will improve because of that action. So we have to, because of the limited computing time, we have to do it 20 and 40%, but other scenarios can be done as well. Next slide. We not only do air quality forecast in Delhi, we have also started an experimental air quality prediction system at NCAR. This is for various purposes. The main reason is that we want to understand the errors and biases in our forecast into our modeling products and how we can improve them, because NOAA is the official agency for making air quality predictions over the US. But these forecasts, they can also be useful for policymakers because they provide additional piece of information on top of what NOAA is providing. So if both the models are telling you the same thing, then you can put more confidence into these air quality forecasting systems. And this is a snapshot of our website where anyone can go and get access to these forecasts. This is publicly available. In addition to providing forecasts, we also provide near real-time evaluation of ozone and PM2.5 against EPA observations. So in this map here, you see on the left ozone from EPA observation, and on the right, ozone from predicted by the chemical model. So the most noticeable feature here means, like, we generally talk about high ozone, but you see a band of these low ozone values in the Midwest, and we are also able to capture that in our model prediction. Next slide. We are also supporting the stratospheric intrusion work group and the NASA's tropospheric ozone LiDAR network. So for all the tollnet sites, we create special products for each site for the cross sections of ozone. And this is one example that we show here. There was a day when our NCAR model on the bottom left predicted a stratospheric intrusion. And so NOAA took this information and they turned on their LiDAR and were able to capture this in the observation. So when you are comparing the bottom left and bottom right figures, please just look at the portion in this purple rectangle on the left side. And you can see that this ozone intrusion from the stratosphere, this filament coming into the lower troposphere, and the shape of the filament is captured very well. So with the guidance from our prediction system, the tollnet team has been able to capture several stratospheric intrusion events. Next slide. Okay, so far I've been talking about the air quality for the next 2 days or 3 days, or maybe people are now talking about air quality 10 days in advance. But the models are also useful for us to understand how air quality will change in a global climate. What will happen means we know that we are having global warming. Even if we stop all the greenhouse gas emissions now, our planet will continue to warm for almost maybe another 100 years. Now, how that those changes in air quality in climate is going to affect our air quality, coupled with the changes in emissions. There are policies aimed at controlling emission sources in the long term. There are countries where there is a lot of economic development. So for example, in the US, the emissions are projected to decrease. In India, the emissions are projected to increase by 2050. So these weather, climate, and air quality processes, they are interconnected to each other, and changing one really affects the other. So here, this is an example of a study led by Gabby, which looked at future changes in air quality over the US by 2050. And on the left panel, you see, irrespective of changing climate, irrespective of global warming, the future emission reductions in the US are going to lead to a decrease in surface ozone. So for example, in Denver area, we might see a decrease of about 10 ppb, up to about 10 ppb. But if if we do not control our emissions and only the climate is changing, we are experiencing global warming. Even if we stay at the present day emissions, ozone is going to increase everywhere over the US, as you see on the right panel. And in the front range area, this could be up to 5 to 10 ppb of changes in ozone. And this is seasonal average over the summer. Next slide. So the models, they are useful for several things: characterize effectiveness of pollution measures, assess trends in reported emissions, pollution levels, and human exposure, separate impacts of exceptional events from day-to-day impacts, understand connections between weather and pollution, and many more, like including the impacts of wildfires on weather, air quality, and climate. So to understand this, we have generated a reanalysis for 2005 to 2018 using the WRF CMAC model at 12 by 12 kilometer square over the corners. So as Gabby was telling, that we have this golden age of satellite data over the globe. So we decided that we are going to combine the information from the models and the satellite data and produce a long-term air quality reanalysis over the US. We are evaluating this reanalysis, and there is a website in development for interactive visualization of various societal relevant parameters. For example, criteria pollutant concentrations, key weather variables like temperature and solar radiation, air quality index, human exposure matrix, estimated changes in premature mortalities over this period, and matrix for agricultural impacts. Next slide. This is just an example of the first analysis, whether our reanalysis is capturing the observed trend in MDA8 ozone and PM2.5. So the left panel in this figure are for the model trends, and the right is measured trend. The top panel is MDA8 ozone, and the bottom panel is PM2.5. So our reanalysis is able to capture the measured trends at most of the US EPA surface sites. We do have some ambiguities as well, especially in the northwestern US, which is significantly affected by the wildfires. So if you look closely at the PM2.5 trends in the northwestern, you can see some of the differences between the model and measurements. But apart from that, we have a very good reproduction of trends by our model. Next slide. These are some snapshots from the website that is under development. So on the website, you can go and compare 2 different years. So for example, in the top left, you see PM2.5 annual average from 2005 and 2018. These graphs are interactive. So if you just move your mouse to a particular county, then you will see a pop-up showing the PM2.5 levels. So for example, in this example, we are showing PM2.5 annual average in Lancaster was 18.6 micrograms per meter cube in 2005, which reduces to 9.2 micrograms per meter cube in 2018. There will also be maps of trend analysis. And again, with the same features, you can just move your mouse to a particular county and you can get information about the relative trend. Furthermore, we will have capability to look at the state levels as well. So you can get these bar charts that are in the middle bottom to see how the PM2.5 and MDA8 ozone have been changing in a particular state. We are expecting this website to become public in a few months. Next slide. All right, so these are all the modeling. These are a few examples of a variety of modeling work that we do, but we also use models to assess how well particular measurement techniques work, for example, in capturing methane emissions from well pads. And mobile flux plane method is one of the techniques. What do you do in this technique? For example, you see a methane plume on the right, and there is a mast with measurement sensors at different sites that is mounted in front of a vehicle, and you drive through the measured plume. So the idea is that we start the measurement outside the methane plume to make sure that we start in the background. Then we go through the methane plume, and then we end in the background. So now comparing the measurements in the background versus the measurements in the plume, we can see how much enhancement in methane is there. And there are also wind measurements. So these enhancements in methane are combined together with the wind measurements to quantify methane emissions from a particular source. Next slide. So here is an example of our modeling setup. On the left, you see the domain, but in the middle panel, you see how do we simulate this vehicle track in our model. So when you see the dotted line, this is the path along which the vehicle is traveling. And as the vehicle is traveling, we assumed a 10-meter wind speed, this line becomes solid. And then this is how we try to depict mobile flux plane technique into our modeling system. So you see that we start in the background, we go through the plume, and then we end in the background. On the below this, in the middle bottom, you see as the vehicle is approaching the plume, how fast the winds are changing. So when we are, there is a lot of turbulence that affects these measurements of methane, and those can lead to errors in the estimation of methane emissions. Coming to the left panel, here we are showing our domain setup, but also 7 oil and gas production wells that we assumed are present in our domain. And you can see that the pad 1, which is the bottommost pad, there is no emission source upwind of this pad. And the emission sources, and sorry for the small fonts here, the emissions from the pad 1 are the strongest. So other pads like pad 4, 5, 6, 7, these are actually located downwind of pad 1. And in the mobile flux plane technique, you just measure downwind of plume. So it is very important to understand what are the consequences of not measuring upwind sources. And this is what we show in the bar chart on the right side of the slide. So here, this is retrieved emissions in percentage. And these synthetic drives that I show in the middle panel, we do it at 5 distances: 50 meter downwind of source, 75 meter, 100 meter, 125 meter, and 150 meters. And these 5 charts are corresponding to these distances. So you can see for all the pads, the red is the highest. It means the closest you are to the source, the better will be your emission estimate. As we move away from the source, we are going to capture less and less emissions because the emissions disperse and concentrations gets lower. Another thing is that pad 1, so there is no source upwind of pad 1, we are never able to reach 100% emissions. So with the mobile flux technique, mobile flux plane technique, the best that we can do is maybe capture 75% of the real emissions that are coming from a oil and gas production source, and that even in the absence of any upwind source. If you look at, say, for example, pads 5 and 6, the emissions are very small, but you can see we have a huge overestimation of emissions because we are not accounting for the upwind emission sources. So it's not only important to measure downwind, maybe in the mobile flex plane method, we should have 2 mobile vents operating upwind and downwind of a source to correctly capture the emissions. Plus, the measurement height for mobile flex plane method is limited to 6 meters. And we have seen many situations, which we are not showing here, where this height is not enough to capture the whole plume. They apply a Gaussian approximation to kind of reconstruct the lost plume. But this Gaussian approximation does not work well in turbulent situations. So I think it's a good technique, but it needs to be complemented with a lot of other things to get correct methane emission estimates from oil and gas production fields. Next slide. Okay, so the final thoughts are like, there are no perfect observations or model products. We need to use them together. We need to interpret them together and this interpretation has to be accompanied by scientific knowledge about the strengths and limitation of each of the methodology. And there must always be an accurate assessment of uncertainties. So research can provide tremendous value to inform the decision making. And we presented a few examples today. You can see that even though our air quality forecasts are not the best, but they provide information about the tendency whether or not air pollution is going to be bad or poor. And that information itself is very useful for the decision makers. So we, in order to solve a problem here on the bottom right, we show an iterative process. We need to define the problem, define the root causes of the problem in the second step, develop potential solutions, and then select a solution, implement this solution, and then in the final step, evaluate the outcome, but continue this loop unless we, till the point that we solve the problem. So with this, I think we would like to thank you and take any questions, and sorry for taking a bit longer.
No, thank you so much, Gabi and Rajesh. This is very interesting. I think we can talk about it for a lot longer. Greg, I think you have a question there. Do you want me to read it, or do you want to kind of verbalize it yourself?
No, I can just repeat it there, Sergio.
Sure.
Thank you very much for those presentations. Nice to see you again, Dr. Pfister. And so with the geostationary satellite tools that will be coming online, do you think we'll be able to resolve this question around local versus regional contributions? I mean, I think about the long-term drought in the West, and depending on which way the wind's blowing, somebody's going to have a wildfire going on. And, you know, I think that sometimes we become desensitized and like, well, it's just the wildfires, right? And we'll never know. And I'm optimistic that it looks like we'll be able to try and identify that in the future.
I think we will get a much better handle on it, clearly. I think the complication is still when you look at ozone, the satellite, you will have more data, you will have much more characterization that you can put into an analysis, but ozone will still remain tricky to really distinguish how much ozone comes from a wildfire, how much ozone comes from other sources. Did a wildfire actually increase or decrease ozone in an area? You know, when you have a lot of thick smoke and you reduce the sunlight, you actually can decrease ozone. So at some point, it will be another piece in the puzzle, but you still will need ozone modeling and a lot of other data analyses to really get at the source of the problem. And again, you know, there is a lot of other. Yes, you have a satellite instrument that will give you some ozone in the free troposphere. It will also give you more information about nitrogen oxides and aerosols. But again, the big piece that's still missing is volatile organic compounds.
Thank you.
Thanks for that question. Any other questions? You can feel free to kind of unmute yourself, or you can put it in the chat. I'll ask one question to Rajesh as we're waiting for others to do the same. You mentioned that you give a forecast in India and you say, okay, the air quality is going to be like troubling. So then there's certain implementation steps. And in one of your slides, you showed that when it's severe, you close brick kilns, hot mix plants, stone crushers, coal power-based power plants. So yeah. my question is, like, when you close the power plants, does that affect the electricity available to the people?
So Delhi gets a lot of electricity from power plants outside Delhi as well. So there is a coordination between the states that are neighboring to Delhi. In fact, now the government has moved out all the power plants from Delhi into the other states for this. So now there is only 2 power plants that are operating within Delhi's city limits, or maybe they even have moved out. So it is only those power plants that are located in Delhi. So, but they continue to get a lot of hydroelectric power as well as coal-based power from other states.
Gotcha. Okay, thank you. Yeah, that was a question I had. And Gabi, you mentioned about the Tropomi that it was able to measure really high methane emissions, 12% of the global. So that's very, very large. And you mentioned that it was very easy to solve those issues. So I don't know if you could go into, like, once they looked at the problem, like why were they emitting so much methane?
I think this was a lot of, and you know, I must admit, this is not a study that I was involved in, but it was basically, it's a lot of leakage. So some of those, it's just basically you make a methane release, you just let the natural gas go out. And they just showed that if you would implement simple measures to capture the methane rather than releasing it wildly into the atmosphere, you could actually make a lot of money. You know, it could be cheaper than just losing this methane in the air. And honestly, I think if you look at the current energy price, I think there will be more and more interest into, you know, not just letting your energy get out the window, so to speak.
Yeah, absolutely. Yeah, I know that sometimes when they're doing the well pad, they just flare the gas, So, but then once you have the site in place, yeah, there must be that there are a lot of leaks and other types of fugitive emissions.
But fixing those leaks can be actually really a financial gain.
Absolutely. No, and I see this as a global LDAR program, like a leak detection program. If you have the satellites looking at the globe and looking at where there's a problem, then we can say, hey, there's something going on, kind of look into it.
Right, and that's the satellite data. And there's actually at the moment also a field campaign going on where they're looking at the future EDF instrument and testing that on an airplane to see how well could that characterize certain leaks and methane issues. So the campaign is called Methane Air, and actually, yeah, it's flying around as we speak.
Awesome, great. Well, thank you very much. I'll give another chance. Anyone else has any questions that you have for our speakers today? Okay, well, hearing none, Gabby and Rajesh, thank you so much for participating in our panel. This was very informative. It was extremely interesting. We look forward to hopefully having you in the future so you can continue to share a lot of this research that you're doing.
Well, thanks a lot for having us.
Yeah, thank you, Sergio, for the opportunity.
And yeah, if there is any other questions, as I said, our contact info is at the last slide, or just, everybody, Sergio, people can get a hold of me, or Rajesh.
That's right. Okay. Well, thanks, everyone.
Okay. Bye.
Thank you. Bye.
Bye.